Good morning, everyone. Thank you for coming in again. What we are going to do today, we are going to go through chapter 4. Here we are talking about superposition. I'm going to provide some examples. Then I'm going to say how and under what conditions we can do a touch-up on the topology and change a bit of the topology, but we have to be very careful as what we mean by that change. That would be source transformation, and eventually we're going to expand the idea of source transformation to the Thevenin-Norton techniques. We provide some examples. We go through maximum power transfer, and that's a condition we would easily find resolved by Thevenin-Norton idea. And then at the end, we have tutorials. As part of the tutorial, I'm going to go and talk about an important structure, easy but important structure called bridge. And then we go and try to solve as many questions as we can, particularly those that are not assigned. Now let's begin with the topic of superposition. Now, in order to see what we are trying to do, first of all, take a look at this circuit in front of you. You have a voltage source, you have a current source, you have two resistors, and you have an interest in finding the V, which is the voltage across the 4 ohm. So what we typically would do is to have, for the nodal, we would typically assign a ground or reference node, and then we begin by identifying the nodes. I have one node here, I have another one. This is going to be one node to me, so I have 2 nodes so far. Considering the reference node, I'm going to have 3 nodes. Now, this 6 volts is going to help me identify what the voltage of this node is. 6 volt is equal to the plus side minus the minus side. The plus side is going to be my X, and this is Vy, so basically Vx minus the minus sign is attached to 0. Therefore, I can say the voltage of node X, the voltage of node X or the voltage of node Y is going to be 6 volts. Okay. So I have 3 nodes, one of them reference node, the other one is obviously identified as Vy as 6 volts. So if I know this voltage, typically, not all the time, typically I don't write a nodal equation for that. So let's go ahead and write the nodal equation for node X, this one. So it's going to be Vx is the biggest one, Vx minus 6 volt divided by 8 ohm, plus Vx minus 0 divided by 4 ohm, plus basically the 3 amp is actually entering the node, so it's going to be minus 3 amp as equal to 0. Obviously, when I solve the system, whatever happens to be my Vx is going to be the voltage V, because this V as an unknown is equal to the plus side minus the minus side. So V is equal to Vx minus 0, V is equal to Vx. The reason I tried to write this equation is I wanted to alert you to the property of this equation. If you take a look at this, you can see that the coefficient of Vx is always constant, a scalar value. Vx is 1 over 4, Vx is 1 over 8, and obviously all the constants are going to go on the other side. So in that sense, for example, this one is going to be Vx, 1 over 8 plus 1 over 4, and then I'm going to take this to the other side, 6 over 8, and then that would be plus 3. It's going to be one equation, one unknown. But this equation is linear. By that, I have indicated a number of simple properties. For example, if the right-hand side is doubled, which would be the excitation coming into the system, obviously my Vx is going to be doubled. If I have more than contributions of one source, what happens in a linear system is that the 2 sources are going to combine their efforts together and get and basically have the voltage across the 4 ohm resistor. I wanted you to see that these equations by no means are nonlinear. They are not going to be a power of 2. We are not going to have Vx times Vy. We don't have e to the power of Vx. This is a completely linear system for this course. Obviously, we would have at some later stages, we are going to see circuits which will not be linear for us. Let's begin now by understanding this linear property. Let's begin now the concept of the superposition. Imagine a Canadian family, something that very easily resonates with people in Canada. You have a gentleman who has married with a lady. And these two have kids, kids alpha and beta. Now A is a person who works at Pizza Hut, for example. And B is a lady who works at Canadian Tire. Now if you take a look at the family income of this set, the family income of this set would be whatever the gentleman brings to home plus whatever the lady brings to home under a simple contractual agreement. That would be the complete family income, and from that family income you're going to start spending money for the purpose of, for the good of the family. Now alpha is a child and beta is a child, and both parents would like to contribute to the college fund of one of these, for example alpha. Now you can imagine, depending on the responsibility, the load that the family has in terms of mortgages, in terms of restaurants and all that, what happens is that A is going to say, I'm going to have my 5% income, 5% of my income to go to the college fund of alpha, and B is going to be saying, I'm going to have 3% of my income to go to the college fund of alpha. So if I take a look at alpha college fund, I am going to see two different contributions. One contribution is coming from the A salary, another contribution is coming from the B salary. It may not be exactly the same, it might be proportional to, depending on the other typical loads the family might have. The contribution on alpha is going to be the summation of this contribution alone, 5%, plus 3% of contribution of B. I can say, I can identify 5% separately, and then 3% separately, and then add them up as the college fund of alpha. Let's map this to the circuit I have. This is a gentleman and this is a lady. Now in his own way, he's trying to bring in energy to the system. Through that energy there would be some voltages and currents. In her own way, she is going to bring in energy to the system. Now this gentleman is going to eventually come in and have some contribution as the voltage across the 4 ohm. When I'm talking about the contribution of 6 volts, I'm not actually considering this. It's independent. They don't actually necessarily overlap. Each one of them can be identified separately. So this one comes in, has a bit of a contribution. If this one doesn't exist, I can calculate that. Then I'm going to have this one off the chart, and I'm going to see how this is going to contribute. I'm going to find contributions of 6 volts for this, provided this source is not there. Contribution of this across the 4 ohm, provided that the 6 volt is not there. This technique that we just talked about is called superposition. In order to achieve this, we need to have some ground rules. Suppose you have a system which has n independent, I insist, independent sources. Obviously, when one of them is dependent, the story is different. So at this time, I'm going to say n independent source I have in the design. I'm going to have n minus 1 sources set to 0, shut down to 0. I am going to find contributions of the nth source. What's the contribution? So in this case, as you can see, if I happen to have 10 sources, I'm going to have 9 sources set to 0. And I'm going to find the contributions of the 10th component. Now, after I did calculate that contribution, I'm going to change the role now. I'm going to combine everything together. Another 10 is in front of me. This time, I'm going to pick up a different source, and I'm going to shut down the rest of that n-1 source to 0. Next time, one more source, and shut down n-1. Each time, n-1 is shut down to 0, but each member takes its position once at a time. So I'm going to see n different topologies, and through each topology, I'm going to find the contributions of that specific source on that specific variable of interest. So at the end of the day, when I have n contributions, I'm going to have all n contributions summed up. N contributions summed up. Well, I'm going to be very careful in terms of polarity, in terms of direction. Obviously, we would like to have added responsibility in terms of college fund. So if they are actually coming in and give me plus minus, this one is giving me plus minus, and this one is giving me plus minus, I'm going to add them up. But you can also imagine a scenario for whatever reason is that one person is trying to contribute to the college fund, but the other person, for any reason, might be removing money from the college fund for any reason. So basically, if this is plus minus for this, and this is plus minus for that, obviously we have opposing values, and obviously we have to consider that as subtraction. So if they are adding together, it would be plus, 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 plus. If they are opposing each other, it would be plus, minus, plus, minus. So that's what we are going to do. Now, what do we mean by setting a source to 0? I'm going to explain this, and then I'm going to go ahead and solve this simple design and move ahead with some complexity and see how it goes. Back in chapter 1, when we talked about current source and voltage source, we said what happens when you have a current 0. If this is your current source, and I say this current source is equal to 0, we said that this current source simulates the behavior of a broken tunnel. So you have a tunnel, and this tunnel is actually broken. Nothing is going to happen with it. People come in, but there is nothing they can do. It's a broken tunnel. I is 0. The number of people per second is going to be 0. Since number of people per second is 0, this is going to act like an open line. So if I wanted to emulate this, it's going to be an open line. If I is equal to 0, it's going to be open line. I would recommend initially to replace the current source with an open line so that our mind gets used to it, and then obviously you can play with this however you like at the end of the day. Now, let's take a look at the voltage source. If you have a voltage source as equal to 0, what does it mean? What is the voltage anyway? The voltage is the energy each individual needs to pass through a tunnel. Now obviously at some point when you take a look at a tunnel with physical geometry and all the constraints involved and all the issues involved, what is happening? You have frictions, you have resistivity in front of you. If you want to pass through the tunnel, you have to spend energy. That's going to be the cause of what we call voltage. When you say a person can go through a tunnel but requires no energy, what kind of example comes to your mind? Well, if you have something that is in orbit, gone to the space, in empty space, and the shuttle is, or the shuttle is actually leaving the Earth and Earth gravity, and there is no other force that is going to prevent it. It's moving without little to no energy. One of these shuttles are actually leaving the solar system way beyond Pluto. So they have gone, they didn't need any much of the energy. So it is possible to go through a tunnel without an energy. One more chance, let me explain this, because this is a question raised last time, and that is, imagine you have a tunnel, and imagine that you have actually floored the tunnel with soap, and imagine there is someone standing here. Now you can actually skate through the floor. So basically you can escape through the tunnel with little to no energy. You can still go, but the V is going to be 0. The V that requires you to go. So I'm going to say the tunnel exists, but you don't have to have much of an energy. It's really much the same as what we have, and it's called wire. So if you have a voltage source, this voltage source is going to be replaced by a short line. I'm going to change that with the color. So it's going to be replaced by a short line. This is short. This is one wire. I replace V as equal to 0 by one wire. So here it is. Here is an example. You have two independent sources. One of them is a voltage source, another one is a current source. What do we do when we face with the idea of a superposition? So let me go back and begin the process. The process is relatively friendly. All we have to do is actually draw the design n times. If you have two independent sources, I need you to draw the design. Draw the circuits. So I'm going to keep this first, and I'm going to shut down this to 0. This is a current source. Shut down to 0, it means it's going to act like an open line. So let me begin. The first one is going to be 6 volt, 8 ohm, 4 ohm, and then broken line. And I mean it. It's a broken line, meaning it doesn't actually attract or allow any current to go through. When I get to this stage, I'm going to call this plus minus V1. It's only the portion of the money that is basically deposited as the current fund of 4 ohm sun. Okay? The second circuit, you have two independent sources. You need to actually bring me the second design. The second design says shut down this to 0. When you shut down this to 0, you're going to have a short on this position, in this place. So I'm going to say this is my second scenario. It's 8 ohm. This one is going to be 4 ohm. This one is going to be the 3 amp. And it's a short. This one is actually, I'm going to magnify, that's a short. That's a voltage source shut down to 0. What is the voltage across the 4 ohm? This is what I would like to see. But I'm going to call that contributions of the lady to the college fund. So this is 3 amp, and that's the contribution coming only from the 3 amp. That's what it means, only from one source. Then obviously you have your chance to play with this design and find each contributions individually. So this is the design in front of me. You need to see this properly now. At this stage, with the mature stage we are in, you need to see how the system is actually working. This is 0. I'm going to remove that. That's going to go a long way to clear the picture for you. Please do that. If the current is 0, you can remove it. As soon as you can remove it, you can see that these two are in series in front of 6 ohm. So what is my V1? I can actually use the library we talked about, and that is voltage divider principle. So I'm going to have V1 is equal to our rule we call 4 plus 8 times 6 volt. So this is going to be 4 divided by 12 times 6. It's going to be 4 divided by 2. It's going to be 2 volts. 2 volts is only the contributions of the 6 volts across the 4 ohm. You can do a mesh if you like. You can do a nodal if you like. As soon as you say, I'm going to separate these sources and find their contributions individually, you can go ahead and do mesh, nodal, super mesh, whatever you have in mind. This one. Now we are at the stage that we can see 8 ohm is actually in front of 4 ohm, and therefore it is in parallel. Take a look at this 8 ohm. I can actually grab it. This is a rubber band in my mind. I grab it and bring it in, and you can see 8 ohm and 4 ohm are actually facing each other, head to head, toe to toe. Therefore, I can see 8 and 4 to be in parallel. I have a current source. That reminds me of a principle I learned in chapter 2, and that is a current division principle. Now, if I find this current, I'm going to know what my V2 is. Let's take a look. Now, the first question I would like to resolve is this. How much is this current? I'm going to call this I2. Time Scott, the direction of this current, the direction of this current, everything else is actually matching with my library. So it's going to be I2, the 0 is equal to 1 over 4 divided by 1 over 4 plus 1 over 8 times 3 amp. So it's going to be 1 over 4 divided by, this one is going to be, I'm going to have 8 as my common denominator. That's going to be 2 plus 1 times 3. It's going to be 1 over 4, 8 times 3. 8 comes on top. It's going to be 2 divided by 3 times 3. And therefore, this is going to be 2 volts again. Hopefully, we made it right. So, 1, 4, 1, 4, 1, 8. That's going to be 2 plus 1, 3. 8 comes on top. I'm going to have 2. This 3 and 3 is gone. Yes, we are fine. But this is 2 volts, and that's the contribution of 3 amp. I'm sorry, this is 2 amp. That's the mistake we have. This is going to be 2 amp. The unit is amp. Okay. Now we found the current that goes through the 4 ohm. How much is V2? V2 is equal to 4 ohm times the 2 amp, and that's going to be 8 volt. That's my V2 now. That's my V2 now. So I need to be careful as to, is this the current? It's going to be amp. I'm looking for a voltage. This is going to be volt. I need to be careful in terms of the units. So I have 8 volts due to the 3 amp, and I have 2 volts due to the 6 volt. But keep in mind though, for the entire process, I maintain the same polarity as the original one. So this is plus minus, plus minus, plus minus. Since I maintain the original polarity, it is now safe to say that the V total, that is the V I want to find, is equal to V1 plus V2. V1 is going to be 2 volts plus V2 is going to be 8 volts. Direction is the same. That's going to be 10 volts. And it makes sense. A good portion of 6 volts is falling on this, and due to the 3 amp that comes in, obviously I have another good portion, and they are together about 10 volts. That's the concept of superposition. I want to go in and I want to have a number of examples from the inside the text, or perhaps at the end of the book, and we'll see how it goes. Let me grab one example. 412. Let's take a look at this. The main application of the superposition is at a time when the system is a bit complex, and that would be something you would learn in EAS 612 or ELE 302. At this time, the system is really simple. 4.12. I have 4 amp. Five ohm, 6 ohm, 3 ohm, 12, 4, and 38. I just picked this randomly, so I'm hoping that everything turns out interesting. 3 ohm, 12 ohm, and the voltage of interest, or the current of interest, doesn't matter. In this case, the voltage of interest is this one. How do I start solving this? It's easy. The first thing I like everyone to imagine is actually to draw 3 different topologies. You have 3 independent sources, and you are asking you 3 different topologies. Each time, you need to keep one of them alive and shut down the rest to 0. Keep this one alive and shut down this to 0. Keep this one alive and shut down this to 0. So let's begin with 3 different topologies. I want you to keep this one intact. So it's going to be plus minus 24 volts. The resistors obviously stay where they are. This is 5, 3, 12, 4. I've gone as far as I wanted to go in terms of the resistors and the single source. My next question is, if I turn this, set this to 0, what happens? This is a current source. When I set this to 0, it acts like an open line. So this one, it goes up, and it's open, nothing is there. There is no current, it's a broken tunnel as if it doesn't exist. I'm not going to draw that. When I take a look at this 38 volt, it's a voltage source. I'm going to set it to 0, so as soon as I do, it's going to be replaced by a short line. This is 4 ohm. That's one topology. The second time, let's keep this one alive and let's set this to 0. And see what happens. I'm going to have this one plus minus 38 volt. I'm going to go as far as the topology allows in terms of resistors. That's going to be 5, 3, 6. Okay. Obviously, when you get to practice a bit, you don't have to do these steps basically as a combination of all 3 graphs at the same time. You can actually put one, solve it to the end, put the second one, solve it to the end, put the third one, solve it to the end. So that's the way we do it when we have a very comfortable relationship with the design and approach. I kept this alive. I'm going to shut down this to 0. That's a voltage source. Because it's a voltage source, it's going to be replaced by a short line. But since this is a current source and I'm setting this to 0, it's going to act like an open line. And therefore, I don't have to draw that. Let's go, and the last thing I want you to do is to keep this alive and shut down this to 0. So if you keep that one alive, you have a current source. That's the current source. Five ohm. You have a 4 ohm. 12. 3 ohm. 6. Okay, so this is the resistive network. What's the decision? This is the voltage source. When you set it to 0, it becomes a short line. This is another voltage source. When you set it to 0, it becomes a short line. In this course, please, when you have these 3 topologies, you should not have two sources at the same time in each one of them individually. One source is only, please. Of course, there are other combinations of superpositions, and we are not talking about it. I would like you in this course to have one source at a time. If your design has two sources, you made a mistake in this class. Okay? I'm not done yet. What am I looking for? VO. VO is the voltage across the 5 volts. I'm going to be conscious. I'm going to assign the same polarity, and I'm going to call this VO1. The same direction, same polarity, I'm going to keep it. And if it becomes negative, I'm going to take it. If it is positive, so be it. So I need to find VO1, VO2, and VO3 and sum them up. And that would be the total VO I'm looking for. So I'm going to have this rule written down separately. VO is equal to VO1 plus VO2 plus VO3, provided that the polarities match the polarity I have on this end. Let's remove this space and let's begin solving one design at a time. Now, as soon as you separate these three topologies, they are different topologies now. Although it looks like they are similar, they are different topologies. So I need you to have peace with the technique you want to do. Whether you want to do mesh, you want to do nodal, you want to compress and decompress, reduce this design and basically come back, that's your choice. Mesh, nodal, and compression, decompression, and the same thing is true. You just need to know what you're looking for, and if you're doing, for example, compression and decompression, secant reduction in one sense, you just need to keep a track of it and come back. I want to do secant reduction using this one. See what happens. I am now mature enough to see 4 and 12 are in parallel. They see each other in one end and they see each other on the other end. We need to make that decision relatively fast because we don't have time to make a mistake. 4 and 12 are in parallel. 4 ohm in parallel with 12 ohm, and the result is, I'm going to call that R equivalent. How much that is? Let's go with the G rule. 1 over 4 plus 1 over 12. That's going to be 12. 3 plus 1, that's 412. Now, I need to remember one more inverse. R equivalent 1 is equal to 12 divided by 4, that's equal to 3 ohm. Only for two resistors, and please keep this in mind, make a red line underneath. Only for two resistors, this relationship can easily be shown to be equal to the multiplication of 12 and 4 divided by 12 plus 4. Only for two resistors. You can multiply and divide by the summation. So this is 48 divided by 16. That's going to be 3 ohm. What did I do? I simply said 4 and 12 are in parallel, and I'm going to replace it, if you don't mind, with a resistor. So this one is going to be replaced with one resistor. That's 3 ohm. In this process, I also noted the fact that VO1 is still visible to me. Whatever I did on the right of the design, it's really not harmful to my entire goal. The goal is to find this one. So I'm going to keep that as a simplification step. Let's take a look at the next stage. I'm still trying to do compression and decompression. This time I can identify 5 and 3 are going to be in series, but as soon as I put them as one resistor, I know I lost VO1. I need to keep a track of it. So it's going to be 6, it's going to be 3. As soon as I say this one is 5 plus 3, you're more than welcome to do that, but you lost VO1. Okay? That's why I'm going to let it go like this. The next time I'm going to have 6, and I'm going to have this one. As I said, because this is only two resistors, I can enjoy the simplicity of 3 times 8 divided by 3 plus 8, and that's 24 volts. This one is going to be 24 divided by 11, almost 2.1, something like that. So what am I trying to do? I have two components in this series. If I find this voltage, what did I find in my previous stage and what do I need? This voltage is the voltage across this resistor. This resistor is coming from parallel combination. Since parallel combinations maintain and preserve the voltage, this is going to be Vx I'm looking for. I am coming from two series coming into this resistor. Because these are series, I remember that the current in series are the same. So I need to find this current that I'm going to call Ix, and I'm going to have this as my Ix. Why? Because VO1 is equal to 5Ix. It's a game plan. You need to devise that game plan and basically go ahead from a stage to a stage. Let's find Vx. Vx is equal to, I'm using the voltage divider principle, 2411 divided by 2411 plus 6 times 24. That's incoming voltage. And this is going to be almost 2. This is 2 plus 6, 8. 2 divided by 8. This is going to be 3, so it's almost 6. I'm just making a guess because I don't have access to the calculator. Okay? If anybody has a Casio, I can actually use that and get a better reading. 24 divided by 11 is going to be 2.18. 2.18 divided by 2.18 plus 6 times 24. Let's see. 2.18 divided by plus 6 times 24. We've got 6.4. So that's going to be 6.4 volts. Okay. I've got this voltage, 6.4 volts. So this is 6.4 volt. I need this current. I need to divide it using the Ohm law. 6.4 divided by 8. That current is going to be 0.8 amp. Since I have 0.8 amp, VO1 is equal to times 5. It's going to be 4 volts. At this stage, I want you to take a note. You are solving one question in the exam, and that is a superposition. And from that exam question, you can see you divided it in 3 sections. You are using compression and decompression. You need to identify which one are in series, which one is in parallel. You need to see where are you coming from when you move from one stage to another. Are you going from parallel to the resistor? Are you going from series to the resistor? All this decision, all this calculation in the midterm exam has to happen in almost 5 minutes, less than 5 minutes. You have 20 minutes per question. So, and imagine 20 minutes divided by 3. You have something like 6 minutes per sub-circuit. So you need to see why it is so important for us to identify this at the conscious level. You can't just pick them out anymore. You have to do this very fast. I found the contribution of 24 volts across the 5 ohm. Let's go back and let's consider the second circuit, this one. But I can enjoy similar approach. I can do a kind of a circuit reduction and come back. 6 and 3, if I reduce them, I'm not going to harm the VO2, so I can reduce this and make it one simple case. Because it's only 2 resistors, 6 times 3 divided by 6 plus 3. That's going to be 18 divided by 9 is going to be 2 ohm. Only for 2 resistors we can do that. So I'm going to actually remove this and replace it with 2 ohm. Okay? Now, because at the next stage of my circuit reduction is going to basically take VO2 inside the entire process, I'm going to lose it. So I have to have a kind of a tracking system to track where it goes. 2 and 5 are in series. 2 and 5 are in series. 2 plus 5 in series, and it's going to be 7 ohm. That's 1. And then you have 12, and then you have 4, and then you have 38. You lost VO2, but we need to go back, so I'm going to keep this. 7 and 12, they are going to be in parallel. So because it's only 2 resistors in parallel, I can actually enjoy the simplicity of 7, 12, 7 plus 12. Only for 2 resistors once again, I insist that you make sure you are not applying this any other way. So this is 38 volts, and this is 4 ohm coming from the previous structure. Let's see how much this is. 7 times 12 divided by 7 plus 12 is going to be 4.42. 4.42. What am I trying to do? As I said, because of the practices you guys have done, obviously you need to have a game plan. I have 2 resistors in front of a voltage source. I want to find this voltage. Let's call this Vy. I'm going to call this Vy. But what is this? Where is this when you go back and you want to backtrack your steps and see where you are coming from? This is Vy across the resistor, and this is coming from parallel structures. And in parallel structures, the voltages are the same. So this one is going to be my Vy, and this one is going to be my Vy. The voltage of a parallel structures are the same. Now 2 plus 5 would be the series combination of 2 ohm and 5 ohm. This 7 ohm is coming from series. So I need to find this Iy. Where is my Iy? If you want to go back and say where my Iy is, my Iy is coming from the top of the 7 ohm down to the bottom of the 7 ohm. My Iy is this way. It's very important for you to see this. Now you need to tell me how much VO2 is. Remember the polarity I insisted in the first place, and remember the direction you got. VO2 is equal to, you need to reverse this in the Ohm law. If you want to follow this for the Ohm law, you need to keep in mind a reversed value, so it's going to be minus Iy. If I know what Iy is, I have a 5 ohm, the other way around, that's the way the current has to go. The current in Ohm law demands that the current goes from the plus to the component and actually leaves the minus polarity. So I'm going to find Iy. Iy is still going to go and manifest itself in my original design, but I'm looking for plus minus, so basically the Ohm law dictates to me the direction that I need to look for. So let's find it. How much is my Vy? My Vy is going to be found through the voltage divider principle. This one is going to be 4.42, 4.42 plus 4 times 38. Let's find it. 4.42, and please don't go more than two digits. Even 2 digits sometimes might be too much. Your answer might be off by some level, but we are okay and we accept the close values as well. So this one is going to be 19.95. So this one is going to be 19.95 volts. It makes sense because 4.42 is almost 4, so this is 4 and 4 in front of this. It's going to be half of that. That makes sense. It's one easy way of making sure your values are okay. You found the Vy. How much is Iy? Iy is equal to the Vy divided by 7 ohm. Vy is 19.95 divided by 7, 2.85. That's going to be amp. This is 2.85. That's going to be my amp. How much is my VO2? It's going to be 5 times minus 2.85, and the result is 14.25 with a negative sign. I'm going to actually make that red. Okay? As long as you say that I have assigned the polarity in my original circuits the same way as I expected it to be, if your value becomes negative, you have nothing to fear. You just simply add them up at the end of the day. So that was my second design. Let's go and consider the last design. Okay. The last design, still you can enjoy compression and decompression. But you need to see the design in a proper light. This is my point of interest. Again, everything comes at the subconscious level now. 6 and 3, do you see them as parallel? Yes. 6 and 3. If you take this, and this is a rubber band, push it in, this wire is going to stretch itself in your mind. 6 and 3 would be in parallel. Do you see 4 and 12 in parallel? Yes, 4 and 12 also can be simplified. So as long as you are not playing with VO3, you can easily shrink the design, and you don't have to keep even a track of it. So this one and this one. My point of interest is plus minus VO3. I'm going to say so. And how much is this one? This one is 6 times 3 divided by 6 plus 3. It's going to be 2 ohm. This one is going to be 4 times 12 divided by 4 plus 12. That's going to be 48 divided by 16, 3 ohm. Once again, I can see how to reduce this design. I can see 2 and 3 would be in series. Therefore, I'm not still touching the VO3. Therefore, I can actually reduce this design to 4 amp, 5 ohm, and since 2 and 3 are in series, that's going to be 5 ohm again, and my voltage of interest is VO3. You need to remember the library, and you need to remember it very well. This is the current. The current comes in. It sees 5 ohm and 5 ohm in front of itself. The people who come in, half of them go through this, other half go through this. It's like 2 lines of passports in when you come and land in Canada. These 2 lines are exactly the same. Which way you go, it really doesn't matter. It's going to get you to the other end of the passport agency. So basically you come in, 5 ohm and 5 ohm. You do expect that the current is going to be divided in half. It's very easy to verify that using the current division principle, because these 2 resistors are the same. But my point of insistence is this. Are you giving me the current with the direction I want, or are you giving me the current that is opposing the direction I want? If this is plus minus, I would like this current to go this way. The current has to go this way in order for me to apply the Ohm law. So I'm going to say, how much is this current? I'm going to say I3. I3, according to the G rule, is 1 over 5 plus 1 over 5 times 4 amp. That's going to be 2 amp. And obviously, after that, I'm going to say VO3 is equal to, because I3 and VO3 are in the same direction that I need according to the Ohm law is 5 times 2. That's going to be 10 volts. What did I do? It was a lengthy process. I broke down the design into 3 sub-circuits. I studied each one of them however I wanted. I found the contribution. First contribution is 4, the next contribution is minus 14.25, and the next contribution is 10. I simply need to go in, and I'm going to apply this. VO is equal to VO1, 4 volts, VO2, minus 14.25, and VO3 is 10. So 4 minus 14.25 plus 10, and that's going to be minus 0.25. Okay? I'm going to solve more problems on the superposition when we get to the tutorial scenario, but I hope I made my point as how the technique works. The technique is this: if you have 10 independent sources, you are going to deal with 10 independent different topologies. Each time, one source at a time is going to be in that sub-circuit, and every other source, independent source, is going to be set to 0. If the voltage source is set to 0, that's going to be a short line. If a current source is set to 0, that's going to be an open. And then I'm left to my own devices in terms of what kind of technique to use to basically solve the design. You solve them if you maintain the direction, if you maintain the polarity in all these 10 different circuits. You can put them together and sum them up and get the whole contributions. By this, I'm going to say the topic of superposition is actually concluded.